Hi everyone. Yeah, the organisers for making this happen despite all the obstacles. So, because one of the aims of this talk was to kind of get to grips with technology, what I want to do today is distinguish between the two places. And the roughly speaking, what I want to argue is that numerical retrocausation is really hard to make what it takes in a coherent way, but all at once retrocausation works quite nicely, and I think so. I'm going to advocate that those of us who work on retrocausation perhaps are moving more towards the all at once conceptions and should be measuring that than we currently have to. I'm also going to explore some of the consequences of that for the kinds of arguments that typically use retrocausation in, and in particular, I want to understand what that means for the idea that types of retrocausality I have in mind are as follows. By dynamical retrocausality, I mean approaches which kind of postulate two separate and mostly independent dynamical processes going in opposite directions. So, for example, the two-state vector formalism, if taken literally, would look like dynamical retrocausality. We have a forwards evolving arrow and a backwards evolving arrow. The alternative is what I refer to as all-at-once retrocausality. And that's the kind of thing we get in models where we think of the laws of nature as applying all at once to the whole of history at the same time. So the example I like to use for that is a game of Sudoku. The rules of Sudoku apply to the whole square all at once. They don't start from the left and evolve towards the right. You might solve the Sudoku in some order, but that order is not specified by the laws, and there's no particular order that matters. The solution is the same no matter the order. So what I want to emphasize about that case is if you take two squares in a game of Sudoku, obviously the numbers in those squares will stand in some relation to each other. The rules constrain how they're related, but it's not the case that one number causes the other or vice versa. They just stand in some kind of symmetric mutual reciprocal relation. And similarly, in an all-at-once approach, we'd expect the same kind of effect. We'd expect the past to affect the future, and vice versa. They would stand in a symmetric reciprocal relation, but we wouldn't necessarily expect to be able to separate that out into two separate and independent directions. So examples of that kind of model include Lagrangian models, and I would also classify Adlam's final measurement model in this box, although maybe you can tell us later whether he agrees with that. I should also note that one might perhaps have questions about whether this kind of symmetric reciprocal relation is really causality. And I would have sympathy with the idea that perhaps we should use some different terminology there. But for consistency with existing literature, I'm just going to go on using the term retrocausality in this talk. So when we postulate retrocausal models of quantum mechanics, those models are normally set out in the context of an individual experiment, often a Bell experiment. When you're focusing on just a single experiment, it's kind of quite easy to make either of those types of retrocausality work, because you can sort of independently postulate a final state and initial state and then bring them together in some way. But obviously, experiments have to be embedded in a broader reality in some way. And once you start doing that, it becomes a bit more difficult to make retrocausality work in a sensible way, because the final state and the initial state will both have to be influenced by both the past and the future. And we end up with situations where you can get those causal loops, contradictions, and all sorts of difficult things. So what I want to do now is consider two sort of very general pictures of, metaphysical pictures of the nature of reality and the way in which things come into being, and try to understand how these two types of retrocausality could fit into these pictures. So the first picture I'm going to consider is sometimes called dynamic production. That's a picture of the content of reality where we think of the universe as being produced sequentially, step by step, sort of starting at the beginning of time and evolving forwards. Or plausibly, one could imagine starting at the end and evolving back, or some combination. But the key point is that it happens in some kind of dynamical sequence. So first off, I think it's reasonably clear that if this is the kind of picture you'd have in mind, you can't really employ all-at-once laws and all-at-once retrocausality, because all-at-once laws, by definition, apply to the whole of the universe all at once, and therefore they can't really be applied in this kind of sequential fashion. So dynamical retrocausality seems better suited to this picture, but we still run into problems because the notion of production kind of entails ordering. If A produces B, we expect A to exist before B in some sense. So So if you want to have a model which combines forwards causality and backwards causality in this kind of picture, you seem to have a circularity where you need the past to exist before the future and the future to exist before the past. And it's like this whole process can't get off the ground. So one way to avoid that problem would be to invoke what I would call mutable timeline retrocausality. That terminology is taken from the philosophy of time travel, where it's common to distinguish between mutable timeline time travel, where the time travelers are able to change the past and thus the present, like in Back to the Future, and immutable timeline retrocausality, where time travelers are not able to change the past because whatever actions they take have already been taken, like in Harry Potter and the Prisoner of Azkaban. So if we allow we could have a retrocausal analog of mutable timeline retrocausality, where we would allow retrocausal influences to change what has already happened in the past. And that would potentially allow us to make retrocausality work in a dynamic production picture, because we could imagine a scenario where, say, the universe evolves up to some time, and then a retrocausal influence is sent back in time, and that makes some changes, and those changes are then propagated forward into the future. So that would be a way to accommodate retrocausality in this dynamic production picture. But obviously this is going to lead to a variety of paradoxes. It's well known that mutable timeline time travel does that, and a famous example is the grandfather paradox, where a time traveler goes back in past and kills his own grandfather before the grandfather can father children, so he is then not born, and therefore he can't go back in time and kill anyone. And one can imagine a retrocausal analog of that, where somebody uses a retrocausal influence to kill one of their grandparents, and thus they're not born, and then they can't see the influence. So because of these kinds of paradoxes, mutable timeline retrocausality seems fairly unappealing. I don't actually know of anyone who really seems to seriously advocate it. That said, it's important to note that, as Hugh showed some years ago, the kind of retrocausality involved in retrocausal models of quantum mechanics is specifically the kind of retrocausality that can't lead to paradoxes like this. And that's basically because that retrocausality can't be used for signaling. So that does take away some of the pressure on this kind of model, but there still are some remaining questions, because the model has to be carefully adjusted to make sure that there is no possibility of causing these kinds of paradoxes. And the natural way to explain these kind of paradoxes is to impose some kind of consistency constraint, as, for example, we would do in the study of closed causal loops. But we can't really have consistency constraints in a dynamical production picture, because consistency constraints apply to the whole distribution at once, rather than being applied moment by moment. So it becomes very hard in this kind of dynamical picture to explain how it is that we avoid all these paradoxes. And in any specific model, it would seem that the model could have been just slightly different, and we would have run into logical paradoxes. The only reliable way to avoid that is constraints. So in conclusion, it seems to me that dynamic production metaphysics is just very difficult to combine with retrocausality, and that therefore, if you are keen on retrocausality, you're better off moving to an alternative type of metaphysics. So the obvious alternative is a block universe type picture, where we think of the course of history as being instantiated eternally and timelessly in an all-at-once manner. That has become quite popular recently, not least because it seems more consistent with relativistic physics than the dynamic production model. So it's easy to see how all-at-once retrocausality would work within this picture. We simply have our all-at-once laws assign probabilities to entire courses of history, and then some history is selected and instantiated all at once in a temporal manner. But what about dynamical retrocausality? Can we have that in this picture? So the typical way of accommodating dynamics in an all-at-once picture, in a block universe picture, is to think about dynamically possible histories. So we set out some collection of dynamically possible histories, and we require that the actual history is selected from one of the dynamically possible ones. But that is quite hard to do if we're trying to combine both backwards and forwards dynamics. And the problem here is that a history is not an intrinsically directed object, right? History is just a history. So if you specify two separate sets and say one is the forward dynamics and one is the backward dynamics, it's kind of unclear what exactly we mean by that, or why we should think of one set of histories as going forward and the other set of histories as going backwards. In addition, even if you can specify those sets in some way, you then have a pretty serious problem of trying to reconcile them and figure out how to decide on what actually happens, given that you have these two separate sets of dynamically possible histories. And Maudlin has an objection, makes essentially this objection in the context of the transactional interpretation, he worries that in an experiment where we allow that the final condition could depend on some of the things that happen in the experiment, it looks as if the transactional interpretation would give rise to a contradiction. And Maudlin further asserts that this kind of worry will apply to all retrocausal accounts of quantum mechanics because they lack any structure which would give rise to a coherent mutual adjustment of the forwards and backwards dynamics. So for what I've said, it should be quite clear that Maudlin's objection in fact applies specifically to dynamical retrocausality, which indeed lacks such a structure because the forwards and backwards dynamics are supposed to be independent. But it doesn't apply to all-at-once retrocausality because the whole point of an all-at-once model is that everything is adjusted coherently and mutually all at once. So you can't possibly have these kinds of contradictions arising in that scenario. So in that sense, all-at-once approaches are much easier to implement and don't have all these kinds of problems that Maudlin brought up. And indeed, looking at the solutions that have been proposed to Maudlin's problem in the context of transactional interpretation, to me, they all look like kind of moving in the direction of all-at-once retrocausality rather than dynamical retrocausality. So in conclusion, it seems to me that if you want retrocausality, by far the best way to do that is to move to a block instantiation picture with all-at-once retrocausality. Dynamical retrocausality in both of these metaphysics ends up causing really serious problems. So moving to all-at-once retrocausality is good because it stops us having to deal with all these objections like Maudlin's, but it does also have some consequences. And in particular, it has consequences for the argument. It has consequences for the argument that we can use. For the idea that we can use retrocausality to rescue locality. And the reason I say that is that to me, there's a sense in which an all-at-once model is just automatically non-local in essence. And that's because in that kind of model, we assign probabilities directly to entire distributions of events across the whole of reality. So what happens at a given space-time point doesn't actually depend on what information is present at that space-time point. It depends on the whole rest of space-time via this sort of global distribution. And that means that in this kind of model, there's sort of really no need for information about one part of reality to be carried to other parts of reality via physical vehicles propagating either forwards or backwards in time. You can, of course, put in such paths if you want to. You can have systems traveling places carrying information, but those paths are in a sense just aesthetic. They're not really doing anything. And Ruth Kessler, I think, makes what I take to be a fairly similar point about the problem of sort of inert, apparently local paths in these sorts of models. So in my view, once we move to all-at-once retrocausality, which, as I say, I think we kind of have to do, it doesn't make a great deal of sense to really focus on retrocausality as a way of restoring locality, because this type of retrocausality is just not really local. I also think that's not a great loss, because I think the motivations for wanting a local theory don't really hold up in this particular context. So I'm going to go through here a list of possible motivations one might have for wanting a local theory and explain why I think they're not very good motivations in this particular setting. This list is of course not exhaustive, so if anyone has any other motivations they'd like to bring up later, please feel free to do so in the questions. So one reason one might like to have a local theory is the idea that locality at a macroscopic level is needed to explain the locality of the macroscopic world. And yes, the locality of the macroscopic world certainly needs explaining, but I don't think this explanatory strategy works very well. And that's because if you are using a retrocausal model to explain violations of the Bell inequalities, that retrocausal model could also, prima facie, be used to create much more widespread violations of locality. So, for example, if you're allowing retrocausality and you allow unrestricted retrocausality, we could always create violations of signaling by sending a signal into the future and back into the past. So what is explaining the apparent locality of the macroscopic world in these sorts of models is not the fact that they are local, it's the fact that there are restrictions on what kinds of influences we're allowed to send it backwards into the past. In particular, the fact that we're not allowed to send retro signaling, for example. So it's those restrictions which are doing all the work in this explanation and not the locality of the underlying model. A similar model which is non-local but which has the same restrictions on what kinds of signals can be sent would provide an equally good explanation of the locality of the macroscopic world. So in that sense, I don't think the locality is really helping in this sort of desire to explain. Another point that's very commonly brought up is the idea that we should have a local theory because we want to have consistency with relativity. So what you mean by consistency with relativity will presumably depend on what you take to be the really crucial content of relativity. But often in this context, what people mean by it is that they think there shouldn't be any preferred reference frames at any level of reality. So it's true that many non-local theories do have preferred reference frames, and that's because they try to institute non-locality by having either a collapse or an update, which is supposed to happen instantaneously everywhere, and thus they have to identify some preferred hyperplane on which that collapse can take place. But non-locality in all-at-once models doesn't take that form, because an all-at-once model is not trying to do things in a temporal sequence. So there's no need to have locality taking place instantaneously, non-locality taking place instantaneously everywhere on some hyperplane. That feature is an artifact of the desire to make things happen in some sequence of temporal evolution. If you simply assign probabilities to whole distributions of events, there's obviously no need to introduce a space-like hyperplane in that way. So kind of the reason why local theories are relatively covariant and have no preferred reference frame is because they are based on continuous time-like paths, which are of course relativistically covariant objects. But continuous time-like paths are not the only relativistically covariant objects. Another type of relatively covariant ontology would be simply a distribution of point-like events governed by an all-at-once distribution. And indeed, we have such a model. The Bell Flash model is an example of such a model. It's defined entirely by point-like events, which stand in some correct relations to each other, and those relations are direct and not mediated by anything passing between the events. And that model is relativistically covariant, provided that we think of the events as being distributed all at once, and we don't try to give an account of the temporal development of the events. So in that sense, consistency with relativity, while it is of course an important goal, doesn't really favor local theories over all-at-once non-local theories, because all-at-once non-local theories are also just as relatively covariant in that sense. The final motivation I want to mention is sometimes people seem to want local theories because they want to be able to use some particular kind of ontology. So, for instance, if you want an ontology based on particles, then it would be quite natural for you to want to have a local theory, since kind of a defining feature of particles is that travel along local paths, local continuous paths. But this to me just kind of seems like getting things the wrong way around. I don't think we should be deciding our ontology in advance and then trying to adjust science to fit our preferred ontology. We should be looking at the physics and trying to figure out which ontology is most consistent with what we see in the physics. So that I just don't think is a very good argument for motivation. So having said all that, although I don't advocate adopting retrocausality to rescue locality, I think there are also many other good reasons to like retrocausal models. And what I'm going to do now is argue that if we just accept the existence of non-locality and we continue to insist that there should be no preferred reference frames, we also end up with retrocausal models. So to see that, let's start by supposing that there are indeed no preferred reference frames in the universe at any level of reality. And let's also suppose that when we perform an EPR experiment with our two entangled particles at a space-like separation, those correlations are explained by a non-local influence between the two particles B and C. So note that there's no relativistically covariant way to decide whether the non-local influence here goes from B to C or vice versa. That's because there's no relatively covariant way to say which order these take place in. If we want to put them in some order, we have to choose a preferred reference frame. So if we are determined to not have preferred reference frames, it seems the only non-local account we can give of this experiment is one where there is a symmetric reciprocal relationship between those two events. The outcomes of measurements B and C must just be coherently mutually adjusted to fit the desired Bell correlations without it being the case that one causes the other or vice versa. I'm now going to invoke something called the onto-equivalence principle, which I think we discussed a little bit yesterday. That's the idea that when possible, we should assume that two processes which produce the same operational statistics can be attributed to the same kind of underlying mechanism. So note that in this EPR experiment, the operational statistics will be the same, regardless of whether B and C are at a space-like separation or whether C is in the future likelihood of B. So the onto-equivalence principle says that we should think the underlying mechanism is still the same, even if C is in the future likelihood of B. So in that case, we should still say there's a symmetric reciprocal mutual relationship between those events, which means that B is having an influence on C in its future light cone, and C is having an influence on B in its past light cone. So in that sense, we have an instance of retrocausality. So note that this is of course, this looks like the kind of all-at-once retrocausality I've been discussing, and not like dynamical retrocausality. So again, one might question whether it's really causality in a strong sense, but it is at this kind of all-at-once model where we have influences between the past and the future. So in conclusion, I think that those people who work on retrocausality would really benefit from making explicit the distinction between these two types of retrocausality and being clear which one they're talking about. And obviously, I personally advocate moving towards all-at-once retrocausality. Making it clear that that's what we're talking about will save us from having to continually deal with objections like Maudlin's, which are really objections to dynamical retrocausality and not all-at-once retrocausality. I also personally think that once we do that, these retrocausal approaches will look much more compelling if we stop focusing on locality quite so much. So that doesn't mean we shouldn't make models which look local. In an all-at-once non-local model, we do still have to find some way of writing down the influences between different events. And it could well turn out that the easiest way to do that is to write them down in the form of continuous pass-through space-time. So I'm not against those kind of models, but I do think that locality shouldn't be the main emphasis, and we shouldn't be sort of scared off by retrocausal models which are not completely local in this sense. So yeah, I'm very keen to hear what you all have to say, so I guess I will stop talking and see if there are any questions.